from velocity to displacement. If we know the velocity, we can invert this equation to get the displacement by changing the Vx is delta x over delta t into delta x is Vx delta t, just some simple algebra. And thus we can get the position xf, the final position, if we know the initial position x sub I, the velocity Vx, and the duration delta t, under the assumption that Vx is constant, which we'll talk about again. This means we're really back to the idea of saying that the position plot is a line, because this looks like y f equals y initial plus slope times x. Well, x minus x initial. We can turn this around to saying something like y is some constant plus b times x minus some other constant, which is almost and can be made into y equals mx plus b. Now, imagine something that moves at a constant speed of 12 meters per second. What is the displacement from time t equals 2 seconds to time t equals 5 seconds? Well, we invert the equation, as said, and we get delta x is v delta t. So 12 meters per second times the quantity 5 seconds minus 2 seconds, or 12 meters per second times 3 seconds, or 36 meters. Not that surprising, not that interesting. But if we look at it graphically, and we make a plot now not of position, but of velocity on this axis and time over here, then we get, well, the velocity is constant, and the graph of a constant thing is, of course, just a horizontal line. Now consider the part of the graph bounded by the t-axis, which is v equals 0, the velocity itself, called here suggestively a curve, but it's really just a horizontal line, and then the earlier time, t equals 2, and t equals 5. Consider that region, this region right here. This region is, of course, a rectangle, so the area of any rectangle is base times height. And so the area of this rectangle, well, the rectangle has a base of 3 seconds and a height of 12 meters per second. And so we find an area of 36 meters. Go back. So a few things to note. One, I've been saying area because I meant area on a graph. Areas are not usually measured in meters. They're usually measured in a distance squared, like meters squared. That's because in geometry, when you learn that formula and you learn that areas were measured in square units, it was because the axes were implicitly distances. In geometry, we only really have distances as our axes, but in physics, we have many different kinds of axes, and so we might get many different types of areas. If you meant the actual physical area, the square inches or whatever that this graph takes up, then you would call it the physical area, and you would have to distinguish. The physical area of this rectangle, I would need a ruler, and I'd measure the lengths, the physical lengths of these sides, and multiply them, and I would get square centimeters or whatever. Couple of things. Now, if the velocity had been negative, then the graph is below the t-axis. So we're talking about, remember, this is our t-axis, and if the velocity had been, say, minus 12, then we would have had this. In this case, we still use the value of v, and so the area is now a width of 3 seconds, a base of 3 seconds, but a height of minus 12 meters per second. That's a little weird. We'll talk about it in a second. And therefore an area, which was base times height, or minus 36 meters. That's kind of weird. How could we have a negative side? And we have a negative side because we're no longer in the first quadrant, right? All of geometry takes place in the first quadrant, but here we're in the fourth quadrant. We get an area that's still meters, the weirdness we have velocity, but also now negative. But that's okay because remember the area is supposed to be giving us delta x. The velocity is negative, so the displacement should be negative. It's traveling towards the left or towards the negative. So this actually is consistent, even though it's a little weird compared to your earlier classes. All right, these graphs represent the velocity of two toy robots moving in one dimension for a particular time interval. Both graphs have the same time and velocity scales. Again, velocity scales. And they want to know, is the magnitude of the displacement of the robot for the entire time interval in A, greater in A, or greater in B, or the same for both? So we say, well, the displacement is delta x. And delta x is the area on the graph. Now it's no longer a horizontal line. The velocity itself is changing. But it turns out that we're still okay with what we had before. We could still find areas. What we have to look at here, though, is that this area, which is below the graph, below the axis, comes in as negative, whereas this area comes in as positive. But something kind of bizarre happens, which is that the physical area is bounded. In other words, if I consider this physical triangle and this physical triangle, they have the same area. If I try to compute here, because the base here is negative of what this one is, and these are the same, we can count them out, then the two areas would be the same in size but opposite, and so the total area is 0, which is kind of weird. What does that mean? Well, it means the thing has actually gone nowhere. Delta x is 0. So it's back to where it was. All right, it was heading, say, leftward. Let's take positive as rightward as we usually do. So it was heading leftward at some speed. It got slower. It stopped having traveled some distance to the left, but then it started moving rightward and started gaining speed at the same rate. And at this moment, it's going as fast to the right as had been to the left and has covered the same distance, and so it has gone back to where it started. If this was the origin, the object sort of went this way during the outbound and then this way during the inbound. So that's a little weird. For the other problem, for part B, we have that the area is going to be positive in this region, but it's going to be negative in this region. And we can see by eye, and it's certainly true, that this area is less in size than this area. So if we were to kind of sketch this, and it started at some origin like this, it moves to the right some amount getting slower, and then it moves to the left, and it does so getting faster and for more. So it ends up something like this. Its displacement is some large negative number. But in the end, they didn't want just the area, they wanted the magnitude of the area. So I'm going to throw away the minus sign. And so the absolute value of this area is positive, meaning that B, right, it's greater in case B than in case A. Here we want to say, shown below are 6 velocity time graphs for a toy robot that is traveling on a straight hallway. All graphs are the same and velocity on the same velocity and time scales. We want to rank the magnitudes of their displacement. So again, we're going to rank, highlight important words, we're going to rank the magnitudes of their displacement. But we don't have a displacement graph, so we have to remember that displacement is delta x, and it's going to be the area. So we look at each of these things and we say, well, graph A is below the axis and has 1, 2, 3, 4, 5 boxes. So that's an area of -5. And over here we have a triangle, and we can compute, right, the area of this triangle will be positive. It's above the axis. And we can see that it is the area is 1/2 times the height, which is 1.5, times the width, which is 5, or 7, nope, sorry, 1/2 times 3 is 3/4, 15 quarters, or about 3 1/4. So this is 3.75. Here we'll have a negative area below the axis, but we can see that the calculation would be basically the same, 1/2 times minus 1.5 times 5. So this will have minus 3.5. And because we're only talking about magnitudes, these will actually end up being the same. For part D, we have a positive area. It's rectangular and easy to compute. It's 1.5 times 5, which is 7.5. In part E, we have a negative area over here. And we have a positive area over here, but we can see again by the symmetry, the fact that it goes as far below on the left as it goes above on the right, means that we get the kind of bizarre thing that this is 0 area. And then finally, we have a positive triangle. Right? Of course, we're going to impose the end of the triangle here. It's not drawn, but whatever. And this is 1/2 times 1 times 5, or 2.5. So now we can see pretty clearly that we have the largest is D. And then the next thing is A. And then the next thing is B and C, which, by the way, should have been 3.75 here. So let's clean that up a little. And then we end up with F. And finally, we end up with E. Here's the velocity graph of an object that starts at the origin at 0, so x equals 0, at t equals 0 seconds. At t equals 4, the object's position is what? So we can see that it's a positive area, so we're going to get plus numbers out, which is not that surprising. It is an area, right? The position, this is xf, which is going to be x initial plus delta x. But x initial was 0, so 0 plus delta x. So it's just delta x, which is just the area. Here we have a trapezoid, and the area, we can think of it, and I will think of it as 2 parts. Part 1 is the rectangle, and part 2 is the triangle. You can do it any way you want. I'm just doing it that way. The rectangle has area of 2 seconds times 4 meters per second. And the triangle has area of 1/2 times 4 meters per second times 2 seconds. So we have 8 plus 4 meters in both cases, so 12 meters. So we end up with C. Okay, it's no coincidence that this turns out, as we all the way along, that the area is the same as displacement. In fact, it will always be true that delta x will equal the area trapped between the velocity curve and the t-axis. If the curve is not a line, we'll have to find the area some other way. The usual way is to slice the area up into a succession of rectangles and then find the limit as the rectangles grow without bound. This technique is the essence of integral calculus. We'll revisit this technique later. We won't have to do integral calculus, but the basic idea we'll use a lot. You'll also, if you've taken calculus, you might have been nodding your head and then kind of thrown when I said this word, which is the area trapped, and I did that for the following reason. Usually, let's take VT, that's fine. Usually a calc teacher would say it's the area under the curve, and that's perfectly fine in the case where the curve is above the axis, because the area is there, the area under the v curve and above the t-axis. But it's less useful to us, or at least it's potentially dangerous, when the curve lies below the axis. Because here we mean this area, oops, sorry. we mean this area, but the area below the axis is this, which goes on to infinity. All right, so this is below. So we don't really mean that. We mean the area which is caught between the thing and the t-axis, whichever side this is on, we want the stuff trapped between. So that's just my own little thing, and I do it a fair bit, but it's going to be a little different from what you'll hear in calculus, but not noticeably.